Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week, and we're going to be talking about the eye of a hurricane and what is actually behind the formation of that eye. And the end result of this video may actually surprise you, but it is going to involve some math and forces and all that sort of stuff. So let us move forward here and get into this. And first of all, some characteristics about the eye of a hurricane. It is generally clear, or mostly clear from a cloud standpoint, and it's associated with sinking air. And when air sinks, it warms up and it dries out. And so that's consistent with the idea that you would not have much of any cloud cover within the eye of a hurricane. Wind speeds are generally 15 miles per hour or less. In many cases, it's actually just dead calm. There's no pressure gradient at all within the eye. Typically, it's 20 to 40 miles in diameter, but there have been some pinhole eyes. I think Hurricane Wilma that hit Florida back in, I think it was the mid-90s, was an example of that. The eye, I think, may have been 10 miles in diameter or maybe even less than that. So that can happen. They form when wind speeds exceed 74 miles per hour, which is the threshold for a storm being named as a hurricane or classified as a hurricane. And birds can actually be trapped inside of the eye. There have actually been some examples of exhausted birds landing on the masts of ships that are in the eye of a hurricane because they're absolutely exhausted trying to get out of it, and they finally just give up and find a safe haven. And so that was a story I was not aware of. That's pretty interesting stuff. But how does the eye actually form? Well, before we answer that question, let's talk about some concepts that may, and probably do, contribute to all of this. So we're going to talk about two forces, one real and one apparent. And if you want an analogy for this, you know how we talk about the Coriolis force being created by the Earth's rotation? That is also an apparent force, okay? It doesn't technically act on an object to change either the direction or the speed. It's simply something that is, again, an apparent force, which obviously has an influence. It just cannot be defined technically as a force. All right, so we have a counterclockwise spinning object. So we'll say that this is our hurricane in the northern hemisphere. It would rotate the opposite way if it was south of the equator. And at any one point along that path, if the air parcel, if you will, were to continue moving in the same direction as it is instantaneously at that point, it would continue to move straight, okay? But what happens is that you have something called a centripetal force, which acts inward, and it keeps the object, or the air parcel, if you will, moving in a circular path. So it's not changing the speed of the object, but it's changing the direction of the object, and so that makes it eligible to be defined as a force. But at any one point, instantaneously, that object would keep moving straight if it weren't for that force making it stay on a curved motion. Now, there is an apparent outward force, and you have experienced this when you turn your car so that you're going in one direction, you're going to turn onto another road, is that the centripetal force is keeping you on that curved path so you don't run off the road, but you feel an apparent force which is caused by your inertia, your mass, okay, that seems like it's trying to pull you away from that curved path, okay? So again, it's something you sense, but it's not actually a force that is changing the path or the speed. Okay, so that's the centrifugal force, okay? And it's acting outward from the center of rotation. And so in a sense, these two sort of counteract each other. Now, in terms of the math, the equation for both is exactly the same, okay? It's the mass times the velocity squared divided by the radius. And by radius, we're talking about the radius of rotation. So like if you have an outer circle and then you have a radius from the center to that point, then that's the radius, okay? If that curved motion becomes smaller, okay, then the radius shrinks as well, or if it becomes bigger, the radius grows, okay? And that applies, again, to both centripetal and centrifugal. M is mass, V is velocity, and R is the radius of rotation. Centripetal force is directed inward, keeping the object on a curved path. Centrifugal force is an apparent force caused by the inertia of the object. Now, there is also something called the conservation of angular momentum, and you have all witnessed this when you watch a skater, maybe in the Olympics, that they're spinning around, and then as they pull their arms in closer to each other, they spin faster, and then if they expand them out again, then they start to go slower. Well, what's going on there? Well, the equation for angular momentum, and for some reason L is used as the letter for that, in this case is equal to the mass times the velocity times the radius, okay? So L is angular momentum, m is mass, v is velocity, r is the radius. If the angular momentum is conserved, which means it's not changing, and the mass is constant, then think about it. If v goes up, r's got to go down. Or, in the case of the skater, if r goes down, v has to go up, okay? So velocity and the radius of rotation are inversely proportional, where if one goes up, one's got to go down in order for angular momentum to be conserved. And so an object moving, or an air parcel moving into the center of a hurricane is going to be accelerating in terms of speed because the radius is decreasing as it gets closer to the center, okay? Now, the bottom line out of all this, and this is what may surprise you, is the scientists still are not completely sure exactly how an eye wall or an eye forms in a hurricane. This is still open to debate. There have been a number of theories put forward, but a lot of these theories contradict each other, and so there is no definitive answer right now. We know what the thresholds are for an eye to develop, but in terms of the actual physics of what's going on, that is still up for grabs. Now, many believe that the conservation of angular momentum and centrifugal force are key ingredients, okay? But again, no definitive explanation exists as of this time. The air spirals toward the center of rotation, but never actually reaches it, okay? And so as it approaches the middle, then it suddenly rises violently within the eye wall before it reaches the center, and then a portion of the upper level outflow, where the mass is being removed at the top of the storm, actually is redirected inward and then sinks in the eye. So some of the mass is transported outward, okay, but a portion of it is directed in toward the center, and then that air sinks, producing that basically cloud-free and also rather calm environment within the eye. So a very, very interesting phenomenon, and you would think that with everything we have learned about physics over, the many, many years that physics has been studied, that an exact explanation for the formation of an eye of a hurricane would have come about long ago, but it really hasn't. There's still work to be done in this particular area. So if you're a budding meteorologist and you're looking for a research topic, this would be one that you could certainly look into, because as of now, even the brightest minds have not come up with a definitive answer. All right, I hope that made a little bit of sense. So I keep forgetting that I have a blank slide there at the end. I'm going to have to replace that. So that is bonus weather video number 3 for this week, and the next one will be coming up on Monday. And I hope you have a wonderful Friday evening if you watch this before midnight. And if you don't, I hope you have an even better weekend. And we'll talk to you again the first of next week. So take care, everybody. We'll see you later.